For decades, humanity's vision of the universe has depended on a single concept. Point your telescope at a specific target, aim carefully, expose the sensor, capture one moment in cosmic time, freeze it, study it, move on. This method built our understanding of galaxies, nebulae, and the deep structures of reality itself. The Hubble Space Telescope perfected it. The James Webb Space Telescope elevated it to an art form. But in early 2024, something fundamentally different entered operation. And what it showed in its first images suggested that everything astronomy believed about how to observe the universe might have been incomplete. The Vera Rubin Observatory stands in the Chilean Andes at over 8,000 feet elevation. It is not the largest telescope ever built. Its mirror measures 8.4 meters across. That is respectable, but not record-setting. The James Webb's primary mirror spans 6.5 meters, but functions through revolutionary segmented design and infrared sensitivity. Hubble's mirror is 2.4 meters. By the mathematics of telescope size, Rubin should not compete with either predecessor. But size is not what makes Rubin revolutionary. The camera inside Rubin's dome is what changes everything. The camera is called LSST, the Large Synoptic Survey Telescope Camera, and it represents the single largest digital imaging sensor ever deployed in service of astronomy. The specification alone reads like science fiction: 3,200 megapixels. To place that in context, the most advanced smartphone camera today captures 12 to 48 megapixels. Professional photography cameras used by photojournalists and commercial studios operate in the range of 40 to 120 megapixels. No camera on Earth routinely exceeds 200 megapixels. The LSST camera at 3,200 megapixels is not just larger, it is a category beyond what existed before. The sensor itself occupies an area larger than a standard sheet of paper. It must be cooled to minus 100 degrees Celsius because the thermal radiation from the sensor at room temperature would overwhelm the faint starlight it is designed to detect. But the specification that matters most is not the pixel count, it is the field of view. The LSST camera observes a patch of sky measuring 3.5 degrees across. That does not sound like much. 3.5 degrees is roughly 7 times the width of the full moon as seen from Earth. But in the context of a telescope, 3.5 degrees is extraordinary. The Hubble Space Telescope, despite its revolutionary capabilities, observes a field of view measured in arc minutes. Imagine Hubble as someone peering through a hole the size of a pencil eraser. The SLIST camera is like someone opening a window. The field of view is so vast that Rubin can capture areas of sky that Hubble would require hundreds of separate pointings to image in equivalent detail. This capability fundamentally changes what a telescope does. For nearly 4 decades, the dominant paradigm in astronomy was the targeted deep field observation. Astronomers would identify a region of interest, point their telescope at it, and expose the sensor for hours or even days to accumulate photons from the most distant and faintest objects. The Hubble Deep Field, the Hubble Ultra Deep Field, the James Webb Deep Field. These observations became iconic because they revealed galaxies so distant that their light had been traveling through space for over 13 billion years. But this method answers only one question at a time. It is strategy, not surveillance. Rubin inverts the entire approach. Instead of pointing at one location and exposing for hours, Rubin scans large portions of the sky repeatedly throughout the night. A single exposure takes 30 seconds. Then the telescope moves to an adjacent patch. Another exposure. Another move. Again and again. By the end of a single night of observation, Rubin will have captured dozens of different sky regions. By the end of a week, it will have scanned an enormous portion of the observable sky. Over 10 years, Rubin is designed to survey the entire southern sky, visible from Chile repeatedly. Not once, repeatedly. This 10-year program is called the Legacy Survey of Space and Time, and it represents a philosophical shift in how humanity thinks about observing the cosmos. The key innovation is this: repetition creates the ability to detect change. When Rubin captures the same patch of sky on Monday night and again on Thursday night, astronomers can compare the two images pixel by pixel. What moved? What brightened? What dimmed? What appeared that was not there before? In a single exposure, a telescope captures a still image. In repeated exposures of the same location, a telescope captures a movie. And movies reveal patterns that still images cannot possibly show. The first images from Rubin, released in December 2023, demonstrated this principle immediately. One image captured nearly 10 million galaxies in the Virgo cluster alone. Not the brightest galaxies, not the most distant galaxies, nearly 10 million galaxies across a range of distances and luminosities, all in a single exposure. The detail is staggering. Spiral arms of distant galaxies are visible as distinct structures. Dust lanes appear as dark patterns across the faces of galaxies. Gravitational lensing events become apparent, where the gravity of foreground objects has bent and magnified the light from background galaxies. But this was only the opening image. The second image released showed asteroid trails. Multiple asteroids, some small, some larger, had drifted through the 3.5-degree field of view during the 30-second exposure. Because the asteroids were moving relative to the background stars, they appeared as bright streaks crossing the image. Each streak is a solar system object reflecting sunlight. Most are in the main asteroid belt between Mars and Jupiter. Some are closer, some are farther out. The mere fact that Rubin captured so many asteroids in a single frame demonstrates the power of the wide field of view, combined with the unprecedented sensitivity of the 3,200 megapixel camera. The previous generation of survey telescopes would capture a handful of asteroids in similar observations. Rubin captured dozens. The third image showcased stellar nurseries, the Lagoon Nebula and the Trifid Nebula. Both regions of active star formation in the Milky Way appeared in a single exposure with extraordinary detail. The ionized hydrogen gas that gives these nebulae their characteristic colors appears as intricate structures. Dark dust clouds that obscure background light create silhouettes against brighter nebular gas. Young stars embedded within the dust are visible at infrared wavelengths. What is extraordinary is that all three phenomena, distant galaxies in the Virgo cluster, solar system asteroids, and nearby stellar nurseries, appeared in different images released in the same week. The point was clear. Rubin does not specialize. It does not require different instruments or different strategies for different targets. A single camera, a single telescope, operating in a single mode, can simultaneously reveal the universe across scales spanning from objects a few million kilometers away to galaxies over 1 billion light-years distant. This versatility is possible because of the 3.5-degree field of view combined with the 3,200 megapixel sensor. The resolution is high enough to resolve detail in distant galaxies. The field is wide enough to capture numerous galaxies in a single frame. The sensitivity is sufficient to detect faint asteroids at solar system distances. The combination creates something unprecedented. Not a specialist instrument for deep observation of a single target, but a generalist instrument, capable of systematic survey across all scales simultaneously. By mid-2024, the full implication began to emerge. During the initial observations, the difference imaging software running in real time detected something remarkable. Every night, approximately 10 million objects changed state. They moved, they brightened, they dimmed, they appeared where nothing had been detected before. 10 million per night, night after night. This is not coincidence. This is the systematic revelation of an entire category of astronomical phenomena that previous surveys had missed because they lacked either the sensitivity, the field of view, or the repeated coverage necessary to detect change. The revolution is not in the images themselves. The revolution is in the method. For the first time in astronomical history, humanity had constructed an instrument that could watch the sky change in real time at scale. Not occasionally, continuously. The universe was about to be revealed, not as a collection of frozen moments, but as a dynamic, evolving system. And the first images were merely the prelude. The implications of detecting 10 million changing objects every single night cannot be overstated. But to understand why this matters, it is necessary to understand what astronomers mean by change and why previous surveys could not detect it. For centuries, astronomy has operated under an implicit assumption. The universe changes slowly. Stars are born, live for billions of years, then die. Galaxies collide and merge, but on timescales of hundreds of millions of years. Supernovae explode, but they are rare events distributed across billions of galaxies. Comets return on regular schedules, measurable in decades or centuries. The cosmos was understood as fundamentally stable at any given moment. Yes, it changes, but the changes happen on timescales so vast that human observation feels like looking at a photograph of a still scene. This assumption shaped how astronomers conducted their work. If the universe is essentially static on human timescales, then the strategy is obvious. Point at something interesting and study it deeply. Accumulate photons. Extract every detail possible from a single observation. Move on. This deep field strategy built modern astrophysics. It revealed the cosmic distance ladder. It proved the existence of dark energy. It showed that the universe contains far more galaxies than anyone imagined. But this strategy has a critical limitation. It is blind to change. A Hubble observation of a region of sky today and a Hubble observation of the same region 10 years later will reveal some changes. But the interval is so large that the evolution is difficult to track. It is like comparing a photograph of a landscape taken in summer with a photograph taken in winter. Yes, they are different, but the gradual changes in between are invisible. Rubin inverts this entirely. Instead of accumulating photons in a single location, Rubin distributes its observing time across vast areas of sky, repeatedly. This strategy sacrifices depth for breadth and temporal coverage. Each individual image from Rubin contains less detail than a comparable deep Hubble observation. The pixels are the same size, but Rubin does not expose each location for hours. It exposes for 30 seconds, then moves on. The trade-off seems obvious. Less detail per image means less information per exposure. But this intuition misses something fundamental. When images are repeated, the comparative information explodes. Consider a supernova. When a massive star exhausts its nuclear fuel, the core collapses and then rebounds in an explosion that can briefly outshine an entire galaxy. For weeks, the supernova brightens dramatically. Then it fades over months and years. A single observation of a supernova tells you how bright it is at that specific moment. But repeated observations at intervals spanning weeks and months tell you the explosion trajectory. They tell you when it peaked. They reveal the rate of decline. They show whether the light output is consistent with theoretical predictions or whether something unexpected is occurring. The difference is the difference between taking a single photograph of a person's face and recording a video of them speaking. One image contains information. A video contains information plus behavior plus meaning. Supernovae are only one category of change that Rubin will detect systematically. There are objects called variables, stars that brighten and dim periodically. Some variables have periods of hours. Some have periods of days or weeks or years. Long-period variables can vary by factors of hundreds in brightness over months. Previous surveys might catch a variable star in 2 observations separated by weeks or months, revealing that it had changed. But without more frequent observations, the exact pattern of variation remains hidden. Rubin, observing the same sky regions every few nights, will capture the complete behavior of every variable star it can see. The light curves will be continuous. The patterns will be unmistakable. This will enable discoveries about stellar physics that require understanding not just that something changes, but exactly how it changes. Beyond stars, there are transient events in galaxies. Tidal disruption events, where a star ventures too close to a supermassive black hole and is torn apart by gravitational forces. These events flare suddenly and then fade over weeks to months. They were rare discoveries because detecting them required either luck or rapid follow-up observations from multiple telescopes. Rubin will find them automatically, hundreds or thousands per year. Because the survey covers large areas repeatedly, every tidal disruption event in every galaxy within Rubin's range will be automatically detected the moment it brightens above background levels. There are also quasi-stellar objects and active galactic nuclei that vary on multiple timescales. There are eclipsing binary stars, where one star passes in front of another periodically, causing dips in brightness. There are asteroids tumbling through space with irregular light curves as different surfaces catch sunlight. There are novae, where white dwarfs accrete material from companion stars and undergo thermonuclear explosions. Every one of these phenomena involves change, and every one of them was previously detectable only through dedicated observing programs targeting specific objects or through lucky discoveries in archival data. Rubin changes the paradigm. Change becomes the default observable rather than the exceptional discovery. The software running in real time compares each new exposure to the reference image of that same sky region. Anything that is brighter, dimmer, or in a different location triggers an alert. The alert goes out instantly. Other telescopes can follow up. The object can be studied. The phenomenon can be understood. But the initial discovery happens automatically because Rubin is watching everywhere all the time. This systematic monitoring also enables the detection of rarer and stranger events. Gravitational microlensing events occur when a star passes in front of a background star, and the gravity of the closer star magnifies the light of the background star. The magnification lasts only hours or days. Detecting these events requires observing the same sky region multiple times during the week-long window when magnification is possible. Rubin will detect gravitational microlensing events by the thousands. These events can reveal the presence of exoplanets around distant stars because the planet's gravity contributes to the magnification pattern. There are also kilonova events. When two neutron stars merge, they produce gravitational waves detectable by LIGO and Virgo observatories. But they also produce an electromagnetic flash called a kilonova. The kilonova is visible in optical light for only about 10 days, then fades away. Before Rubin, detecting kilonovae required rapid follow-up from multiple telescopes coordinated in real time. Rubin will identify kilonovae automatically by detecting the sudden brightening of a star-like object in previously monitored sky regions. Within minutes or hours, the Rubin alert system will trigger observations from other telescopes capable of detailed study. The implications extend beyond individual transient events. Repeated observations of the same galaxies over years will reveal patterns of activity. Galaxies that are undergoing active star formation will show signatures of that formation evolving over time. Galaxies hosting active supermassive black holes will show variations in the energy output from material spiraling into the black hole. Merging galaxies will show the signatures of gravitational interaction becoming more pronounced as the merger progresses. All of these processes unfold on timescales of years to decades. Previous surveys, lacking the repeated coverage and the sensitivity to detect subtle changes, could observe only the current state. Rubin will observe the trajectory. It will see how things evolve. The full magnitude of this shift becomes apparent only when the numbers are considered. 10 million changing objects detected every single night. Over a 10-year survey, that is approximately 36 billion detected change events. But these are not 36 billion separate objects. Most objects change multiple times during the 10 years. Some asteroids are observed hundreds of times as they orbit through regions of sky Rubin surveys repeatedly. Some variables are observed thousands of times over a decade, creating complete light curves of unprecedented completeness. The result is a dataset where the universe is not just photographed, but tracked. Every moving thing is traced, every brightening event is recorded, every dimming is logged. This dataset will fundamentally change what questions astronomers can ask. Instead of asking what is the current state of this object, astronomers will ask, how did this object get to its current state? Instead of asking what types of events exist, astronomers will ask how frequently do events of each type occur across the entire observable sky. Instead of asking whether a phenomenon is real, astronomers will ask what is the complete behavior pattern of this phenomenon. The shift from still images to continuous monitoring transforms astronomy from a description-based science into a narrative-based science. The universe becomes a story told in motion rather than a collection of frozen frames. And the story is only beginning to be read. The philosophical significance of this shift cannot be separated from its technical reality. For nearly 4 centuries, the telescope has been an instrument of observation. Galileo pointed his telescope at Jupiter and saw moons orbiting the planet. Herschel scanned the sky and discovered Uranus. Hubble measured distances to galaxies and discovered the universe was far vaster than believed. Each discovery came from pointing and looking. But Rubin is not merely a better version of this strategy. Rubin is a different strategy entirely. It is the difference between reading a description of a landscape and watching that landscape through a window as seasons change. Both convey information, but they convey different kinds of information. The conventional deep observation strategy answers the question, what is this? The repeated survey strategy answers the question, what is this becoming? These are not equivalent questions. They do not produce equivalent knowledge. A photograph of a human face answers the question, what does this person look like? A video of that person answers the question, what does this person do? How do they move? What expressions do they make? How do they interact? The video contains the photograph, but the photograph does not contain the video. Similarly, repeated observations of the sky contain the information from single observations, but single observations do not contain the information from repeated observations. Rubin is not replacing the previous paradigm, it is supplementing it with an entirely new dimension of information. The first images from Rubin demonstrate this principle immediately. The image of nearly 10 million galaxies in the Virgo cluster shows the static structure of the galaxy population at this cosmic epoch. But when Rubin observes the same region 6 months later and compares the two images, additional information emerges. Which galaxies have varied in brightness? Which have remained constant? What does the pattern of variation tell about the population of active galactic nuclei? What fraction of galaxies host supermassive black holes undergoing active accretion? These questions cannot be answered from a single image, no matter how detailed. They require the comparison that repetition enables. The asteroid trails visible in Rubin's first images represent a different category of information. A single observation shows that asteroids exist and they move through space. Repeated observations will show the precise orbits of thousands of asteroids. For asteroids whose orbits were previously unknown, Rubin will determine their trajectories, their sizes estimated from brightness, their composition estimated from their color, their rotation rates estimated from brightness variations as they tumble through space. All of this information emerges not from a single deep observation of a single asteroid, but from repeated observations of many asteroids captured incidentally as they drift through the survey field. The stellar nurseries visible in the Lagoon and Trifid nebulae show regions of active star formation. But a single observation captures only a snapshot of a process that unfolds over millions of years. Repeated observations will reveal subtler changes, dust clouds shifting slightly as radiation pressure from newborn stars pushes them, brightness variations in newly formed stars as they contract gravitationally toward the main sequence, outflows from young stellar objects becoming more or less prominent as material flows away from the stars. These changes are slow by human timescales, but measurable by Rubin, because the instrument is patient and systematic in its surveillance. The difference imaging software represents the culmination of this philosophy. Rather than requiring astronomers to manually inspect millions of images looking for changes, the software does the work automatically. Every night, the new observations are compared to reference images created from the deepest, clearest data collected during the survey. The software identifies every pixel that has changed, every object that brightened, dimmed, moved, or appeared where nothing existed before. 10 million objects per night. The sheer volume makes human inspection impossible, but the automation makes human discovery inevitable. No transient event will be missed because the software is tireless. No pattern will be overlooked because the software examines every pixel. This automation also democratizes discovery. In the era of deep field observations, discoveries required access to expensive telescope time and the expertise to design and execute complex observations. Thousands of astronomers competed for a small number of observing nights. The people making discoveries were the people with connections and resources. Rubin data is public. Every observation is released immediately. Any astronomer anywhere with a computer can download the data and search for discoveries. The person making the next major breakthrough might be someone working at a small college with no telescope of their own. The barrier to entry has collapsed. The potential for discovery has expanded beyond the professional astronomical community into citizen science. into crowdsourced analysis, into patterns emerging from the most unexpected corners. The 10-year legacy survey of space and time has been designed with a specific structure. The survey will observe the entire southern hemisphere sky visible from the Chilean Andes repeatedly, not just once but many times. Different regions of sky are observed with different frequencies depending on their scientific importance and their visibility from the observatory location. The galactic plane, rich with stars and nebulae, will be observed frequently, but not as frequently as the deep extragalactic sky, where galaxies crowd densely together. The survey is optimized to maximize the scientific return while respecting the practical constraints of a ground-based facility. Over 10 years, this repeated observation will accumulate data of unprecedented scale. The complete survey is projected to generate approximately 20 petabytes of data. A petabyte is 1 million gigabytes. To contextualize this, the entire human genome sequence is approximately 3 gigabytes. 20 petabytes is equivalent to the genetic sequences of roughly 6 billion humans. A single night of Rubin observations generates approximately 20 terabytes of data. This raw data must be processed, calibrated, cross-matched against catalogs, and made searchable. The computational infrastructure required is itself revolutionary. Data centers must be built. Processing algorithms must be optimized. Storage systems must be deployed on scales previously unnecessary for astronomy. But the computational infrastructure required is itself revolutionary. The 10-year survey will produce catalogs of objects like nothing ever compiled. Billions of galaxies catalogued not just by their static properties but by their behavior over the decade. Hundreds of millions of stars traced through brightness variations revealing their nature. Millions of asteroids tracked through the solar system revealing orbital parameters. Thousands of transient events captured from explosion to fade revealing the physics of stellar death and black hole feeding. The data will answer questions that today seem too ambitious to even ask. What is the complete census of supernovae in the local universe? Not just the bright ones. All of them. Thousands per year. What is the rate of tidal disruption events around supermassive black holes in nearby galaxies? How do asteroids fragment and scatter as they collide in the main belt? How frequently do comets transition from the Oort cloud into the inner solar system? What fraction of stars host long-period companions that remain invisible to other detection methods? What is the complete population of kilonova events in the observable universe? These are not marginal questions. These are fundamental questions about how the universe works, and Rubin is the first instrument capable of answering them systematically rather than anecdotally. The first images released in December 2023 are merely the opening glance, a preview, a demonstration of capability. The real revolution is not in those images. The revolution is in the decade to come, in the systematic accumulation of change across the entire observable sky, in the detection of phenomena so rare that only a survey of this scale can find them frequently enough to establish patterns, in the transformation of astronomy from a science of isolated objects into a science of connected systems and events and evolution. The universe has never been watched this way before. Never with this sensitivity, never with this breadth, never with this patience. The implications are still being understood. The discoveries still waiting to be made are countless. But one thing is certain. The 10-year legacy survey of space and time will change what humanity knows about the cosmos. The first images showed that Rubin can see. The next decade will show what it sees. And what it sees is waiting.